In this lab, we are gonna apply what we learned in the last episode of LLM Chronicles dedicated to LLM agents. So we're gonna see how to implement PAL and ReAct in practice. And I already know this is gonna be an extremely long episode. It might be more than 1 hour long, and I might need to split it into 2 different episodes. But what you are gonna learn here is how to actually build these agents and LLM chains from scratch. You're gonna learn how to play with the different prompt templates, how to extract actions, how to execute them. And this episode is for you if you really want to understand what happens under the hood. And if we look at the list of topics from here, I've actually put all of the timestamps because I know that some of you will just want to jump ahead to the section that's most interesting. But what we are going to do, first of all, we're going to start by implementing PAL from scratch first, and then we're going to use LangChain to implement LLM chains. And we're going to do this with GPT-4o mini, but then we are also going to see how to do these with Llama 3 and Mixtral. So it's going to give you an idea of how you take the same concept and you can swap different models, open source, closed source, and try to play with the prompt templates so that you get similar outputs. After we do that and we learn how to build LLM chains with LangChain, we're going to dive into the most important part of this episode, which is building a ReAct agent completely from scratch first, and then we'll see how we can do that with LangChain. And towards the end of this, we'll also cover OpenAI function calling and the ReAct conversational agents. So this is when you want to take some of these agents that we're building, but add them to a proper chat interface or a chat interaction with the user. So again, without any further ado, let's get started. So we are going to get started with the standard imports. We will be using, first of all, just the OpenAI SDK, and then we'll do the same things using LangChain. So we need to install these packages. I've already done it. And then we are doing some basic imports. And as usual, when you work with a lot of these libraries and SDKs, you want to set the specific environment variables that contain the API keys. And for this notebook, I'm actually using the secrets functionality. So when you get this notebook, you go into the secrets and set the variables, or if you want, you can copy and paste the keys there, but this is obviously not recommended. So once I've got that, I'm just gonna instantiate an OpenAI client, and I'm gonna create a utility function to call GPT-4o mini with a prompt. So that's just obviously a chat model. So that's the typical template, role, user, content, prompt. And now I'm just testing that I can actually run that particular function, which I can. So I get a completion from GPT-4o mini. So now that I've got this, we are ready to implement PAL from scratch. PAL stands for Program Aided Language Models. And the idea is that you can give a problem to the language model, and instead of the model answering the problem by itself, it produces a Python script, which then you go and run on behalf of the model to actually get the answer. Now, why would you do this? Because models are not very good at counting, but they are good at producing reasonable programs, for example, in Python. So the idea is that this would improve the ability of the model to solve certain types of problems, specifically problems that have to do with maths. And indeed, if you go and look at the results in the paper on different benchmarks. There you've got it here. For example, if you compare the solve rate of a model which is prompted or which is using PAL versus something that's just using chain of thought or a simple direct prompt, you will see that the solve rate of these mathematical questions are much higher. For example, on GSM 8K, which is just these grade school maths problems, the model has a 72, or the method gives a 72% solve rate, which is obviously much higher than not using PAL. Let's go now and implement these from scratch. It's actually fairly simple. First of all, we start with the prompt. You can play with it, you can write it yourself and change these, but here I'm simply telling it that it is a helpful assistant that solves math problems using Python programs. And then essentially I provide it an in-context one-shot example of how I want it to perform. So given a problem, I want it to give me a Python code block with the solution. And I specifically tell it, this is important, that after I run the code, I want the result, the solution, to be in a variable called result so that we can go and fetch it. So after the in-context learning example, then in my prompt template, I have the placeholder for the variable, which I'm calling problem. And now if I actually go and run this, I have just a sample problem, which I think I've taken from the paper. We are not going to read the problem. I don't think it's very interesting per se, but I have my problem in a variable and I can obviously replace it in the prompt template. And I get the full prompt that I can then send to the LLM. Now the LLM will process this. And as you can see, it returns the Python block as we described, with a few comments and then the actual code. So the idea would be now to take this and execute it. So let's go and do that. I have a helper function that takes this response and essentially finds the Python code block and extracts the actual code between the code blocks. So that's the first one. And then this one over here simply executes that function using a Python interpreter. Now, I should say, as a cybersecurity guy myself, you need to be very careful when you do this. This is an example, but taking just some random code which an LLM has produced and executing it could be very dangerous. You would need to do this within a fully isolated sandbox. So this goes without saying. But again, here we just have an example. So we've defined these functions here. So now we can take that generated code, execute it with the Python interpreter, and we get the answer 11, which I happen to know is the correct answer for the problem I provided it. So that's essentially what PAL is. Obviously, if you want to make this more useful, you would wrap it into a full LLM chain. Let's do this manually so to understand how all these building blocks could be made usable. Essentially, what we want is a single function to which we can pass a problem in natural language, and then the function returns us an answer. So that's all those steps chained together. That's actually incredibly simple. So that problem, we take the problem, we substitute that in the prompt template, we pass it to our language model, which generates the code, and then we execute that code. So we then extract the answer, which would be this in this particular case, and then we return a string such as the answer is whatever. So let me define that chain, and now I can have a second problem and simply pass it to the chain. And the answer is 74. So you can see how simple it was to actually build a working PAL example. So now what we've done manually, I want to show you how to do with LangChain. And essentially LangChain, as the name says, is a framework which at the core allows you to build these LLM chains in a very versatile way. So to me, an LLM chain, very simply, is a set of steps that are chained together, of course. So you take the output of one step and you feed it to the next step. Now, a common chain typically starts with a prompt template which defines a set of variables. Then the variables are filled in and passed into an LLM, which provides an answer, and then we do something to that particular answer. We will parse it out. For example, we'll take a string out of it, or we'll parse it as JSON, XML. And in our case for PAL, for example, we could even go and execute it. So LangChain makes it really easy to build these chains. They have a lot of interfaces and helper functions that make this trivial, and they have something called LangChain Expression Language that, again, will make it very intuitive to just string together all of these steps in a chain. So the way we can recreate that PAL chain that we did manually with LangChain is by, first of all, importing Chat OpenAI, which is the implementation that LangChain, the wrapper that LangChain provides around OpenAI own SDK and interface. Now, the advantage here, and one of the advantages of frameworks like LangChain, is that all of these things are abstracted with higher level APIs. So as I'll show you in a second, if you want to change from OpenAI to Claude or to literally anything else, like you want to load a model from Groq and stuff like that, it's very easy. You simply just have to import a new package and just switch one line of code. So that's the LangChain OpenAI chat model, and actually I think I've got it open if you want to take a look. But again, for me, the most important takeaway is that LangChain will put in the latest version all of these different providers, models implementation or API implementations inside different packages. So as you see, this is now in a package called LangChain-OpenAI. And if we take a look at that, you will see, and that's my important point, is that ultimately this Chat OpenAI object extends base chat model, which is in the LangChain core. And all of the other providers' chat models will ultimately extend this particular class, which means that they all become interchangeable. So that's the chat model, and that's how you would implement it. So we give it the model name, the temperature, we can pass other parameters as we're going to see later. And as usual, you need to have the API key defined as an environment variable. Obviously, we've already done this. Then we are going to create a prompt template, which comes from the prompts package in the core LangChain library. And this is very trivial. You simply define the template and the same template string that we used before. That works perfectly fine. And then you define the variables that you've got in your template explicitly. So here I'm basically saying these are my input variables. And now we've got all the basic building blocks, and using the LangChain expression language, I can create a chain. So I can start with my prompt, which LLM I want to use and what I want to do with the output. In this case, we're just going to parse it as a string. So I implement that, and then I can take the chain, I can call invoke, and I can pass an object with all the input variables, and these are going to be filled in for me, and all the chain is going to be run. And in fact, if we do this, you can see that the output again is the Python code that GPT-4o Mini has generated. Now, obviously, we don't want to stop here. This is not our full chain. Our full chain needs an additional step here at the end to actually go and execute the code. And adding a step to a LangChain chain is incredibly simple. Each step in the chain essentially extends this core class called a runnable. And that's the interface. So I'm calling this execute Python. And one key part that we're going to implement is the invoke method, which obviously takes the input into the chain and returns whatever is the output of that, which can then be shown to the user or passed to the next chain step. So in our case, this execute Python runnable is just going to be a wrapper around the execute Python code that we had before. So if now I define this and I extend my pal chain by adding this as the final step, and then I invoke it with a problem, this time we should see the full output. So that's how simple it is to implement a custom chain with the most recent version of LangChain using the LangChain Expression Language. Now, I very quickly want to show you how easy it would be to swap this LLM, GPT-4o Mini, for any other LLM. And I've chucked this in the appendix. So you are going to need to install additional packages which obviously implement the APIs or the API calls for the additional LLM platforms. Here I'm going to show you how to use the TogetherAI platform and the Groq platform. If you're not familiar with these, they are essentially platforms which offer API calls to access many open source languages. For example, if we go to Together, you see all of these models here, including Meta, Llama 3.1, 8b, 70b, 405b, and so on. But you see also the other open source models, Mixtral, WizardLM, Llama from Google. So you get the idea. So they implement a lot of these and it's very useful. So let's say I wanted to use these models. As usual, you are going to need to set an environment variable to hold the API keys. Then from that LangChain package, you would import the chat together, which if you go into the implementation, it will ultimately implement the base chat model. And so if you implement these and you pass the name of the model that you want to use in the configuration, then you can create a chain. And you see the only thing different in this chain, these are all the same prompts, the same output parsers, the same execute Python. The only thing I changed is that I swapped the GPT-4o or the chat OpenAI implementation with this client here, and it worked just fine. And indeed, I got the answer. So you see how powerful this is. And now, again, I can do the same with Groq. So that's the Groq API key. And again, Groq is another one of these cloud services which will implement or make available a lot of the open source models. You can see the ones which are available, at least in my account. And just for demonstration purposes, I'm going to use Mixtral 8.7b. And obviously, Together also has that model. So this doesn't make a lot of sense, but I just want to show you how to use Groq. So I import chat Groq, I instantiate it pointing to the Mixtral model, and I create my chain by swapping in the LLM. And it works as well. I should also say that most modern LLMs work really well with things like PAL and ReAct that we're going to see in a second. The final thing I wanted to say on PAL is that here we've basically still created this by hand, but LangChain has a full PAL chain with the prompt templates and the Python executor already implemented for you, so you could use it. And I think it comes from the, sorry, let me just find it. There it is. And it comes from this LangChain experimental package. So you could simply import the PAL chain that they've already implemented for you and pass it the problem, and it will basically do something very similar to what our chain does. The only problem is that at the time I'm recording this video, this generates an error. So I think that they have a bug essentially in their implementation where it's not parsing out correctly the solution given by the LLM. When I look at this, the LLM is giving the correct solution in the right format, but probably the chain that they implemented at some point got broken. But this is perhaps another reason why you really want to be able to do these things from scratch and to understand everything that's going on. Very often you'll find that it's much better to re-implement your own chains and tweak them rather than using the pre-built chains. So we're now ready to tackle ReAct. ReAct comes from this original paper from Google in 2023 called Synergizing Reasoning and Acting in Large Language Models. And you will remember from the episode that the basic idea is to create agents that can think about their next actions, and then they're given a set of tools and they can say, in order to solve this problem, I need you to execute this function, this tool for me, and then give me the answer. So they work in this loop of thought. They are prompted to think about the next step. They call an action or a function or a tool, whatever you want. We go and execute the tool with the arguments that the ReAct or the LLM gives us, take the output of that tool and then pass it back to the LLM as an observation, and then the LLM continues its thought action loop until it finds the final answer. So really, again, this idea of taking the chain of thought reasoning and mixing it with access to tools which allow the agent typically to interact with the external world. Now, what we are going to do, we're going to create a basic ReAct agent, and as usual, we start from the prompt. Now, I shall say that there are a million different ways and different details that you could use to write one such prompt, a lot of different variations, and you should definitely play with it. There is not one ReAct prompt or one ReAct format, and especially if you use modern LLMs that are very good at in context learning, you'll find that you can really play with the structure of these, and they'll typically do fairly well. So for this particular one, I tell it that it is a trivia expert, and then I say that I tell it that it runs in this thought, action, observation loops and what each of the steps are. And then I tell it which tools it's got available. So I'm going to give it a web search tool that takes a query, a calculate tool that basically computes a mathematical expression, and then this is quite important, I'm going to give it a final answer tool. So this is what the agent is going to use to signal that it's completed all of its reasoning and it's got the answer. So I will take the answer which is inputted here and then show it back to the user. And as usual, here I give it an example of how this operational loop works, leveraging in-context learning. So I'm going to provide it a question, and then the LLM will output a thought. I need to search Wikipedia to find the information about the topic. In this case, we're asking how tall the Eiffel Tower is. And then it needs to produce an action in this particular format, in this case, searching the web for Eiffel Tower. And then it's going to receive the answer back as an observation. So this is going to be the content of that web search. And then the LLM should look at that and think, oh, I need to calculate 300 plus 24. This is because I asked, in this example, a more complex question, telling it I want to know the height of the tower, including the antenna on top. And just to show it how it should think, the answer it gets from the web search is not exactly that, but it's got the size or the height of the antenna and the height of the tower. So now the LLM thinks, so I need to calculate 300 plus 24 to give the answer. And then it produces an action 300 plus 24. And then the observation is this. So now it should think, I've got the final answer, and it calls the final answer tool with the string, which is the response that we want to show to the user. Now, obviously, this is a little bit of a contrived example. To be honest, if you ask any modern LLM this question, it's likely to just know the answer by itself. And most LLMs don't need to search the internet for these. And even to do something like 300 plus 24, LLMs are not great at math, but that kind of computation they should be able to do. But it doesn't matter, because here we're trying to kind of get an idea and tell the LLM how we want it to operate. So this is the template within context learning. And then obviously we've got the actual placeholders for the question that the LLM actually needs to answer. And then very importantly, we have an action trace because we are going to build this trace as we call the LLM inside that loop so that it can look back at the actions and the thoughts and the outputs from those actions, deciding when it tries to decide what the next action is. So that's the prompt implemented. And now I'm going to wrap this into a basic ReAct or trivia agent chain. So I'm going to take the prompt, GPT, and then just parsing it as a string. And I'm going to invoke it with a question. When was Gardaland founded? If you're not familiar with it, it's an Italian amusement park. But now, this is key. What's happened here? I asked a question, which was put in here, and the LLM produced a thought. I need to search Wikipedia, produce the action invocation in the correct format, and then look at this. It also hallucinated the observation. Gardaland is an amusement park located in Italy, and it was founded in 1975. Now, obviously, we don't want this to happen. We need to go and do the web search and provide the answer. We don't want the LLM to hallucinate the answer. And obviously, it kept going, thinking, now I have the final answer, and calling the final answer. So the whole point of ReAct is that we're not going to allow the LLM to hallucinate the observation. We're going to stop it here, execute the function on behalf of the LLM, and feed the observation into the context. So a very, very easy way of doing this, in the way that we are structuring this particular instance of ReAct, is that we are going to stop the LLM as soon as we detect observation column. So as soon as we see that it's starting to hallucinate an observation, we stop it there. This is really easy to do because we can pass a stop string or a stop pattern. And so whenever this LLM is now called, LangChain is going to stop it when it starts generating the observation. So that's the same chain as before. I just changed this LLM, and you can see now that if we look at this, it produces the thought, it produces the action, and it's now obviously stopped there. So this stop condition prevents the LLM from hallucinating the observation and allows us to then look at this output, extract the action, go and execute it. Now, something important here is that you need to think about what that stop condition needs to be. And that really depends on the prompt structure that you've given to the LLM and how the LLM is handling it. So giving you a few other ideas. You could, for example, be more explicit with the LLM. So in your in-context learning example, you could actually ask the LLM to produce the word pause or any other keyword that you want immediately after it produces an action. So you could give it this particular example here in the context. And now if you do something like this, then you can take whatever keyword that is and use it as a stop action here. That would work equally well. And obviously you need to experiment with the LLM to see what works best. But again, as I said, typically most LLMs today will do well whatever way you prompt them. Okay, so now we have to extract the action from the output of the LLM. Here I have a simple regular expression that's going to match the action name and the action input. So if we run this and then we call it on that output, we now see that it returns action name web search and the action input Gardaland founding date, which again was this particular line that the LLM produced. And again here, this parsing here obviously depends on the format you've given to the LLM. And as I said, there is no right or wrong way to make a ReAct agent. It just depends on the LLM you're working with and how easily it can work with different formats. But just to give you an idea, if the LLM produced an action like this in the current format that we're giving it, final action, the Eiffel Tower is 324 meters tall, and then it opens a parenthesis to say how much it is in feet. I don't know why it would do that, but let's say it does that. This parsing function is going to break because it's going to see this and interpret it as the end of this final action. So it's gonna cut some of the output of the LLM. So basically what I'm saying here is that this example that I'm giving you in this particular format, in reality, you would need to work with it to make sure that the LLM knows what kind of characters it can produce. And very often, as we'll see later, the LLM is actually prompted to use JSON instead of something like a function call like this. Especially with strings, it can be, again, particularly complicated to parse out. Another idea that you will see for function calls is to actually tell the LLM to split the action and the action input into two different rows or lines. So in your in-context learning example, you could actually tell the LLM to call an action like this, and then on the next line to have action input and provide the input there. And obviously you would change this method to parse that out. And honestly, if you want to get value out of this very long episode, you need to spend time with these. You need to see, okay, let me play with these. Let me change this format. Let me write a parser. Let me see how the LLM handles it, because that's what honestly is going to give you a real feel and practical experience for how much you can play with the technology. But again, for me, this is the nuances which are important to understand when you're creating agents. But now, let's keep this original format, because in this simple example, it still works fine. And what we need to do, we now need to implement the tools which the LLM can call. Here I am implementing a final answer tool, which simply, again, takes the final answer and returns it as a string, and I'm simply stripping some white spaces and potential quotes because I just want the string. But this is just like an auxiliary function that I'm putting there. Then I have a web search, and in reality, this web search would use like the Bing API or any other API to go and actually do a search and return an answer. Here I simply have a mock response, which is going to be useful for one of the examples that we're going to do later. And then I have a function that performs the mathematical calculation. So I'm taking the expression and I am evaluating it. As usual, again, these are examples. There is typically already tools in LangChain which implement this for you, but the idea here is to understand how these things work from scratch. And I should say that from the cybersecurity point of view, again, you need to be very careful evaluating expressions produced by the LLM. Anyway, we now have the tools defined. And what we need to do is to write all of the scaffolding around this to connect the action call that the LLM is making with the actual tool and return the output as an observation. And this would be the ReAct agent loop. So I typically call it an agent executor. It used to be called an agent executor in LangChain. Often people also call it kind of like an orchestrator, which is a general way. So calling the LLM, parsing the output, calling the LLM in a loop, and so on. So how does it work? We implement a loop and we have a max number of iterations. That's actually quite important. You never want to have these loops go on forever. The LLM can actually get stuck, and if it does, you need a way to stop the loop and return an error. So this is what these max iterations is doing. So then we take that agent and we invoke it with the question that's been provided, and this is gonna return that thought and action step. And again, it's gonna stop when the LLM starts hallucinating the observation. So then we're gonna take these and we're gonna use the extract action function to get the action name and action input. And then we're gonna check if the action doesn't exist. Obviously, we kind of like return an error. We say no action detected, and we continue the loop. And it's quite important what's happening here. So we obviously want the LLM to see the output of all the tools. So we have this trace variable, which is part of the prompt template, which is going to be obviously empty at the beginning. But every time the LLM produces a step, thought, and action, and we then produce an output of that action, we are going to add that to the trace so that at the next iteration, that trace can be fed to the LLM. So just to show you again where this is in our prompt, that's where it is. And again, that's going to start building thought, action, observation, prompt the LLM again. It now sees that it's already called some objects and some actions, and it can see the output, and then it can think what to do next. Again, that trace there is the key to actually implementing and making this work. So now, if the action does exist, I call the specific tool with the action input and collect the output as an observation and add that output to the trace here, and again step and trace as an observation. And then I go into this loop until you see the break here, until the LLM produces final answer, which then I take and return. So let's run these and ask a question. Now we can see that the result of 500 plus 233 minus 10 is 723. So this is just the answer, but obviously we would like to see all the trace. So I have another implementation of this React agent executor, but I've just added a debug trace at the end where I am collecting all of these thought actions and observations so we can see what the LLM actually did. So let me implement this, and now we give it the same problem. And this time we can see the debug trace, and specifically, where is it? All right, so that's the question we asked. Obviously, this is the in-context learning, and that's the thought the LLM had, the action it called. This is the output we gave from our tool, and that's the LLM thinking, all right, I have the answer, and then it calls final answer with that string. Now, again, I don't want to spend too much time here, but this is the prompt that we gave to the last iteration of the LLM. So here we are already breaking the loop, and obviously this action trace here, this is the first time we called the LLM, it stopped here. We went and execute the action. We added thought, action, and observation to that trace variable as we do here. We called it again, and so obviously then the LLM had this prompt, this entire prompt the second time it was called, produced this thought and action, and because it's the final answer, we didn't call the LLM again, we just broke, printed this, and gave the final answer. Now let's try a different problem, such as convert $500 into euro, and this should potentially give us a more complex chain. So it first thinks that it needs to find the current exchange rate. So it calls web search, and we give this observation from web search. If you remember, this is the mock response that we hard-coded. That's why we hard-coded that particular one. And now it produces this thought, and it produces the correct calculation. And then we give the answer. Now the LLM has the answer, and it's responding. So as you can see, that's how a ReAct loop works. I want to show you again, as we did before now, that you could take the exact same prompt and loop and just swap in the chain, for example, Llama 3 instead of OpenAI GPT-4 or GPT-4 Mini. I don't remember what I used for that one. So here we're going to use Llama 3.170B from TogetherAI, and again, stop condition, building the chain, exactly the same chain, and then we can call this, and you see that ultimately some of these might be slightly different, but you see it's basically producing very similar thoughts, calling the objects or the tools and giving the final answer, which is still correct. And here you see how you could do the same with Mixtral. Again, this is exactly the same function. The only thing I'm changing is the in the chain we are swapping the LLM. But as you can see here, Mixtral should be able to do that and use the tools correctly and give oh, actually, in this particular case, as you can see, Mixtral got confused, and for some reason it's escaping the underscore when it calls final answer. So now we're feeding this error in, and so now it gets stuck in a loop, and ultimately, after 5 iterations, it stops. So here, let me try to call it again. I'm not sure why it's doing that, but let's try again, see if it's okay. It doesn't like it. What you would need to do here, and I'll leave it as an exercise, is to play with the template and the format of action invocation and how you pass the arguments and the action names to see if you can fix it. This would be particularly useful to actually learn how this works. So as we said before, the format of that ReAct prompt can be whatever. And typically today you would do a JSON format for actions and observations. That's very popular, especially with OpenAI models which handle JSON pretty well because of their fine-tuning and training. So the LLM could be told to output an action as a JSON string, and then we would convert that output into JSON and actually handle it much better. There is in LangChain already an implementation of this, which we're going to see maybe later. But then some other models, for example, LLM, they are actually fine-tuned already as part of their training with specific tokens for describing the tools, the plugins, and invoking actions. By the way, as we said in the other episodes, tools, actions, plugins, all these kind of things are fairly interchangeable. But just for LLM, if you were using that, it would actually produce action start token, giving the plugin that needs to be called, and then passing the methods or the arguments, the name of the tool. And the thing is, you don't need in context learning because it already knows to do this if you prompt it to call actions. What I wanted to show you is that, for example, you could do the same ReAct prompt using XML. Some models like Claude are actually very good historically with XML. And if you go, for example, on AWS Bedrock, which uses Anthropic's Claude models, the agent or agentic framework in AWS Bedrock is actually an XML-based agent. So let's look at how you would do this. So it's the same prompt as before, but here I'm telling it to use these XML tags to describe thoughts, tools, tool inputs, and how it's going to receive the observations. So now if I run this, obviously I need to change my stop action to here. I create a chain with these. Again, I have underscore XML, all of these, so that you don't get confused. But again, if I now invoke this, it works as expected. This is because now a lot of models can handle XML as well as JSON. But then this is just the basic chain. Obviously, I will need to change my extract action because now my action is a tool invocation and tool input between these tags. So I can implement this, and then I can basically take that original agent executor and do an XML version where I simply pass the, again, XML versions of my tools, but the loop stays pretty much the same. Again, just when I inject an observation, I will inject it as a tag. And if I run this, I can ask the same things as before, and the LLM functions properly, but you can see the XML syntax. And again, even these other questions convert $500 to euros. The answer is correct based on the exchange rate that we gave it. I don't even know if it's a reasonable exchange rate, but you can see all of the chain of thought, tool input, and so on. And again, the reason why I'm showing you this is to give you the building blocks to actually create your own agents with your own formats, fixing broken stuff, and being able to use all different types of LLMs and find exactly the prompts and the formats that work with those. Now, to close on ReAct, I also obviously wanted to show you the LangChain implementation of the ReAct framework. So let's open the official documentation for LangChain, and obviously they have a ReAct agent. Let's just go in and take a look at this implementation. Now you will see that here we have a new package called tools. So obviously LangChain needs to implement abstractions around the different concepts as we saw before, and the idea of a tool that the LLM can use is abstracted with these classes here, like basic tool, structured output or input tool, and so on. And then from agents, we have the agent executor and the create React agent function. And so let's look at this. The first thing we're going to do, again, we're going to create the tools. And the way to create tools is to basically decorate them with this tool attribute. And it's really important that you pass the doc string explaining what the tool does, because then LangChain is going to take this and use it to create the prompt and to tell, you see here, obviously we hard coded this in the prompt, but with LangChain, it's going to go through the tools that you pass, it's going to extract the name and the doc string, and it's going to build something like this so that the LLM knows which tools are available. And then we put these tools in an array. The other thing that we're going to do, from the hub of prompts, we're going to take the ReAct prompt that LangChain uses, and we can even take a look at that ReAct prompt. But let me see if I can maybe print it in a little bit prettier format. Okay, so answer the following questions as best as you can. You have access to the following tools. And again, this is going to be filled in with these tools. Then question, thought, action input. So you can see here that the basic LangChain React prompt is using that format. Observation, final thought, begin. I mean, to be honest, this is a much more concise prompt than the one I gave. And then we can just create the React agent with the LLM, the tools, and this prompt over here, and wrap it into an agent executor, which is ultimately going to implement that loop extract the tools calls, run the tools, and so on. So if I create these and then we run it with the problem that we had before, you will see action. So thought to convert currencies, you should always search the web for the current exchange rate. Action, web search tool, input this particular one. And the format is a bit weird here, but this is the output from our tool. Then the thought is now I have the exchange rate, I can use the calculate tool, and so on. So this works fine. And so that's like the basic LangChain implementation for ReAct. You can see here all the other agents that it implements. So you also have an XML agent. I'm not going to show you that, but you can see here works very similarly. There is going to be a prompt, and obviously the example shows how to use this with Anthropic. As I said, historically Anthropic models are better at XML. This is not true if you are using a model like GPT-4. It can do XML fine, but then again it creates an XML agent, and then we wrap it into an executor. Just for fun, maybe we can take a look at that prompt. Let me just run it here, and take a look at that prompt. And obviously we just want to look at the template. So I've had to change that print to this because this is a conversational agent. So it's made of different, obviously, messages, and the prompt template, you need to extract it like that. But you can see tool invocation, tool input, observation. So very similar to what we did. Now I want to show you another way that we can implement agents. What we've done so far with ReAct involves creating a ReAct prompt which shows the LLM which tools are available and asks it to select a tool directly. Now, another way that you could create agents is by leveraging function calling in certain LLM APIs. So you've got providers like OpenAI, which essentially in their LLM completion API will allow you to define, together with a prompt, which could be like a generic question or task, a set of functions. And then the API, so OpenAI in the backend, will select the appropriate function to call, and the parameters, and we return that to you so that you can go and call the function yourself. Now, again, the difference here is that you wouldn't be using ReAct yourself. You wouldn't be passing a ReAct prompt. You just pass a question or a task and a list of functions, and you offload all of that logic of tool selection to the actual API. So when it comes to OpenAI, this is quite simple to do with the SDK. So I'm not using LangChain here. We're just literally using OpenAI. And the way we do that, we simply pass a list of tools with this particular format. So obviously we need the tool name and the properties or parameters that need to be passed to the function. So we create that, and then we can create a chat message. These are typically in chat completion, offered as part of the chat completion endpoint API. So this would just be the individual task. And then when we call the API, we just pass the list of tools. And we can also tell the API whether we are actually requiring a tool to be called, or if we are allowing the LLM to choose whether it wants to just do a normal response or if it wants to call a tool. If I run this and we print the completion, you will see that in that chat completion, because we required it to call a tool, I think if we go down, we'll find a tool calls kind of list, and as part of that we will find obviously that it wants us to call the function calculate tool with the expression 5 plus 10, because obviously that would be the most logical thing to do if you have a calculate tool and you are asked to do a mathematical operation. Now, obviously, what you will need to do here, you will need to take this completion and extract the function call. Here I have a simple method to do that. So if I run this, then we can see tool name, calculate tool, tool arguments, obviously this one here. So then you could wrap all of this up into an agent executor, very similar to the one we did before. So you would have a loop similar to this. Obviously, you'd call the LLM with the question, you would extract the action, you'd go execute the action, and then keep going. Again, the major difference here, or I would say the only difference, is that your prompt will not include the full ReAct prompt. It will just include the questions, and in the backend, OpenAI is going to run whatever custom models they have optimized based on your prompt and the tool list to select the specific tool. And obviously, all of this can be implemented or is implemented with LangChain. If we open this up, we can see the LangChain documentation these days is actually pretty good, and you can typically copy paste, and that's what I did. So you'll see that you can implement a full agent with this. You are gonna pull the specific OpenAI tools agent prompt, but again, you could change it if you wanted. And you have this create OpenAI tools agent that you import from the agent package, and then you wrap it up into an agent executor. So let me create this, and then we can invoke it with our usual sample task. And this should work very similar to the ReAct agent before, invoking the search tool, and then invoking the calculate tool and giving the final answer. So this becomes very, very easy to use. And finally, to close this very long episode, I wanted to talk about chat agents. So what we did so far, the ReAct agents we looked at, are agents to which you give a single task or question, a set of tools, and then the agent executor goes in the background and iteratively tries to answer that question or perform that task by calling the necessary tools until it's got a final answer. So that's not a interaction that you're having with the user. There is one question and one output from the agent. Now, there are many cases where you want an agent to also be able to converse and interact with the user. So you could have a customer assistant agent that the user can talk to, ask questions, and that agent can decide whether to use tools and start a ReAct loop, or whether to keep asking information or interacting with the user. So this is not particularly complex, but you just need to expand your general ReAct agent and agent executor so that it's got that way to decide whether it wants to start a ReAct loop or it wants to talk to the user. And you also need to provide it in the prompts a history of the conversation with the user, not just the tools that it's used. Now, LangChain has a chat ReAct agent, which again enables these dynamic conversations and essentially adds the chat history to the context. So this lives in the typical LangChain core package. So we can pull the ReAct chat prompt, and we can even take a look at it to see what this template is like. And as you can see, there is a space for the different tools and how we should use the tool in ReAct fashion. But there is also the concept of talking with a human. So you have the conversation history and the agent scratchpad. So the agent scratchpad would be the trace that we had in our prompt here. So this would be the trace, you can call it whatever you want. But now, obviously, with this template and an agent executor which is aware of this type of agent, you can actually have a chat conversation. So if we, for example, invoke this agent with this input, and we add to the chat history human, hi, my name is Bob, and then the AI response. So this would be the chat history. Then based on the input and the chat history, the agent can decide whether to start the ReAct loop or to talk to the user. In this case, obviously, it will just go into the ReAct loop. But I think I have another example here where the same agent, I'm asking, what's your name? So in this particular case, it will say, thought, do I need to use a tool? No. So now it can go and give a final answer, which is returned to the user. So hopefully this is making sense. But again, the idea is that when you have a response that you need to communicate to the human, you tell the agent, do not use a tool. You have a response you can communicate to the human, and you provide it the current chat history. Now that chat history here, I cheated and I just provided a string. But if you're using LangChain, you want to build your chat history for consistency using the wrapper objects for human message, system message, AI message. But ultimately, all of these, when you pass them to the agent, they get transformed into a string. Everything going into the LLM is ultimately a string, unless you have obviously a multimodal LLM. And then what you would do, so if you were actually implementing a chat agent, so you do, what's your name, chat history, you get the answer, and then you would add that answer, the question the human sent in the output of the LLM to the chat history. So then you could continue the conversation. So when there is the next question from the user, you are now passing this chat history plus the question. And in this case, again, this should know to use the ReAct loop, because obviously to answer that, it needs to use the tools. Now, in the next video, we're going to take all of these building blocks and we'll build together a few real-world web applications which implement different types of agents. I haven't decided yet, but I think I am going to probably implement a customer service agent which can interact with the user, access the user account, and get a list of the orders and be able to perform some basic actions on behalf of the user. And we might even do an agent that, for example, is able to be a gym coach and make a workout plan for the user. So if you like this type of content and you actually want to learn how to build a proper agent from scratch, like a full web application, subscribe to the channel, because again, in the next few weeks, hopefully I'm going to be able to show you how to do this.